Good morning, everyone. I welcome each one of you for today's lecture. Today, we will continue to look at edges, corners, and blobs. And then we will go on to discuss another important topic called fitting. So, under edges, corners, and blobs, we started discussing mainly about the edge detection. And there we realized that it's the derivative operation that we are talking about. And we were able to design kernels like this for edges. And these kernels are very simple kernels. And afterwards, we came up with these kernels called the Prewitt kernels and then the Sobel kernels. For example, if you take this Sobel kernel, it detects edges of this nature, right? This area is dark and this area is bright. These kind of kernels, these kind of edges. Then we looked at how image gradient, which is a combination of the partial derivative in x direction and partial derivative in y direction, computed using Sobel operator or any other operator, can be combined to come up with the gradient of an image, this nature. So you can see that gradient operation gives you a vector field. So then we looked at detecting edges when noise is there. So think about noise is, although there is an edge in this one-dimensional image, because of this noise, our gradient operation becomes very noisy and gives us noisy output. And therefore, the actual edge that is here cannot be found. So that's why we have to first of all think about smoothing using a Gaussian kernel like that. So therefore, what we do is we take this image, noise image. Of course, this is a one-dimensional image, and smoothen that image. When you smoothen that image, you can see that the noisiness is gone. But rather than just directly smoothing the image first, it is possible for us to get the smoothened version of the uh, Gauss of the edge detecting kernel and then run it. So now here you can see we have taken the Gaussian smooth image. If convol G means the Gaussian smooth image, then you run the derivative operator. But it is not required to do so because you can construct a new operator called the Gaussian smooth derivative, right? Then when you have that kernel constructed, now this represents a kernel, and then you can run that kernel, which is much more less computationally expensive. And I showed you these kernels in pictorial format. So you can see in these kernels also, there is this negative values, positive values nature, as in the, for example, the central difference formula, where we had +1 here, 0 here, and -1 here. And I have displayed that as an image over here. So these are smoothened versions of the derivative kernels, and these are the ones that we must be using. Then we discussed about the separability, and then the scale of the scale of the Gaussian derivative kernel. Scale means a sigma value. Then we looked at these things. For example, if you take the smoothing filters, now smoothing filters are just a blurring that we do with the Gaussians. We understood that they must sum to 1. What is the values within the kernel must sum to 1. But on the other hand, if you take the derivative kernel, the values within the kernel must sum to 0. The reason is, if you take, for example, the white wall, there is no edge within a white wall. So when you run the derivative kernel on a white wall, it must produce a 0 for you. Then we looked at the Canny edge detector, which is detecting the edges followed by somehow thinning and drawing one single line to represent the edge. Yeah. And we looked at this image, and where you can see the so-called hysteresis has been applied to combine the low threshold edges and the high threshold edges. So starting the edges with high threshold edges, strong edges, yeah, and continuing them with weak edges. Okay, so that's what we looked at, and then we started looking at the corners. So these are the corners you can see, and we understood the motivation why we need those corners. We want to align images and so on, and we discussed about four important properties of those uh, features that we detect as corners. First one is repeatability. Repeatability means um, if you take several images, the same corner should be detected in both the images. So here also you can see uh, there are dots to represent corners. So just observe that the same corner has been detected in both these images. These two images are different viewpoints of the same scene, right? So compactness, efficiency, saliency, locality, these properties we discussed. And we looked at some applications and did this fun exercise also. Then we wanted to get the theoretical understanding about the corner detection process. And there we realized that the flat region is characterized by, if you take a small window like that, within that flat region, now this is a dark region in the image, right? If you slightly move it in any of these directions, whatever the direction, okay, there is no change within that window. But if you take this example, for example, this is an edge. In this edge, you can see if you move in this direction, there is no change. But if you move in this direction, the darkness and the whiteness covered by that window changes. So for an edge, no change in along the edge direction, but there is drastic change along the perpendicular direction to the edge. But not so with a corner. If you take a corner, for example, if you move in any of these directions, up, down, whatever, there will be a drastic change in the intensity profile captured by this little window. That's what we want to find. So you will think that in this case, there must be a vertical gradient and there must be a horizontal gradient. This is fine. That idea is fine so long as your corner, as shown here, is axis aligned. Now you can see these edges are aligned with the x-axis and the y-axis. But when they are not aligned, the way to do that is to compute the so-called eigenvalues. That's what we look for. That's why we had to come up with this uh, formulation. When we slightly change the location of the window with this u, and with this v, we slightly change the location of that window, and we subtract from the original image and we get the squared error. So you can see if u is 0 and if v is 0, this will result in 0. But due to a small values of u and v, so here you can see the u and v have been some value because this is the central window, but you can see that green thing has been slightly moved from the center. So that is u and v. Because of that, the intensities do not exactly match with the intensities in the green dotted rectangle do not exactly match with the intensities within the red rectangle. So therefore, there's an error. So we showed that error. So you can see when u and v are 0, there's no error. But when u and v are different values, there are different kinds of errors. So what you want to do is mm, uh, find out how this function behaves for small shifts. So therefore, we want to study this function. In order to do that, we cannot work with this. It's very hard to work with that. So therefore, what we did was we came up with the Taylor, first order Taylor expansion of that. So Ix means x direction derivative and Iy means y direction derivative. And we know that using Sobel operator, how to compute those derivatives of images. So when you put this, so you can see that the IX gets cancelled off because of this IXY gets cancelled off. And then we were able to convert that into matrix one and realize that this matrix is this one. Summation over a window, IX squared, summation over a window, IXIY, same thing, and the summation over window, IY squared. Hmm. This is actually what we call is a convex function. So therefore, you can find a minimum for that without a problem. But if we consider about the axis aligned cases, we said that if either A or B is close to 0, then it is not a corner. So look for locations where both are large in the axis aligned case. But we don't have to worry about the axis aligned case that now that we have the second moment matrix, we can look at its eigenvalues, lambda 1 and lambda 2. When both are large, it is a corner. So I showed you this picture where these ellipses have been drawn with the eigenvalues, these eigenvalues arranged in a fashion like that, right? Okay. Okay, so then we came up with this rule when lambda 2 and lambda 1, these are the two eigenvalues. When they are both large, then you will have a corner. But then we said that computing these eigenvalues is usually computationally more expensive than computing this determinant and the trace of the matrix determinant. You know that for 2 by 2 matrix, determinant computation is very easy. And trace is the sum of the diagonal elements. That's also easy. So this one is called the Harris measure. This was discovered by Harris and Stevens in 1988. So if R is large, it's a corner. If the modulus is R is small, it's a flat region and so on. So, but usually people multiply it by some W also. And with that, you are able to detect corners. And I showed you this picture, cornerness, and how the corners can be finally detected and superimposed on this image. You can see the same corners have been detected in both the images. Okay. All right. Mm. Any questions from that? Now we can start today's material. Any questions from what we covered last time? Of course, as usual, you are most welcome to type any question and ask, um, or else you are most welcome to turn on the microphone and ask questions also. Yes. Okay. So some questions for you. Here there is another problem here. I'm sorry about that. So the first question, if the intensity of the image changes, what that means is you have the intensity of the image, let's say 200, 200, and different kinds of values, 200, 3, 204, like those values. And you multiply those by a small number called A and add B. Will the location of the corners change? What's the answer? So this kind of a thing is called an affine change in the intensity. Will the location of the corners change? The answer is no. The reason is our corner detection is based on the derivatives. Derivatives are not sensitive to the constant values. Even if you add a constant value, they do not change. So the B definitely does not affect this one, but A may slightly affect. But usually it is, we called it invariant to intensity shift. And because of this A, since you are multiplying, some corners that were not there, can appear. So, but slightly is a problem. So partially invariant to affine intensity changes. That's the conclusion from this. Partially invariant to affine intensity changes. I hope it's clear. Now let's take the translation. So you can see the translation means the corner was originally here, and now the corner has been moved to this location in the image. So due to this, if you use this Harris corner detection, will we miss the corner or not miss the corner? I think all of you will realize that we do not miss the corner, we will detect it, but at that different location. So for that case, we can call derivatives and window function shift invariant. Corner location is covariant with respect to translation. Covariant means with the translation, it moved. That's the right thing. That's the right thing that we expected in this case. Okay, now the rotation. What's the situation here? So originally image is like that. Now you can see here there is a rotation. Is this, will this create a problem to detect the corner? No, it will detect the same corner, but the orientation will change. So therefore your eigenvalues will change. Second moment ellipse rotates, but its shape, that is eigenvalues, remains the same. So I lied to you. Eigenvalues do not change, but the rotation matrices change. I'm very sorry about that. Corner location is covariant with respect to rotation. Okay, now the problem is with the scaling. The scaling thing. There is a problem with that. Now let's try to understand that. Now, in this situation, you can see there is some intensity change within that window. So this area is dark, this area is bright or something. So you can see we usually detect a corner there. Corner there. But if you consider this situation, your window size is small, window size is the same as in the previous case, which you use to detect the corner, but your image has been greatly scaled. You can see that's the image structure that has been greatly scaled. Now the question is, will you detect corners? So now if you observe, for example, if you observe this situation here, you can see these are just straight lines inside the corner, right? These are just straight lines within the window. So as you can see here, you don't see a corner. So you see a corner at that right scale. So here the scale is different. So therefore, unfortunately, all points will be classified as edges. Corner location is not covariant to scaling, not covariant to scaling. So this is something that you have to remember. Okay, yeah. So now that's why we introduced the so-called blob detection. Are we ready? Oh, can I move forward? Any questions? Okay. So, since the previous one just mainly continued from the last week's uh, lesson that we started, maybe some of these things you did not understand if you forgot about it, but this one you can understand. It's a new topic. Okay, so please pay attention. Little bit of mathematical thing is there. All right, let's look at this. Now, blob detection means detecting blobs. They are like circles. So you can see in this sunflower field, the blobs have been detected. For example, this one is a blob. See, that has been detected. But when you go far away, the sizes, they change. So definitely you can see we have to detect blobs of different sizes that you can see. That. Yeah. Okay, let's see how to mathematically do this. Now, one thing is there. This is something that naturally happens to images. Now think about you going to a mountain or something, and then you take a picture of this, I don't know what that is, a church or something. You take a picture of that, and you can see it's far away, far away. But then you zoom in your camera and take another picture of that. Now this appears in that circle. Now in these cases, you can see it will be very hard for us to match them, right? Very hard because they are of entirely different scales. Although as a human being, we have no problem in matching them, but the computer just sees a set of numbers. How can you match them? So that's why they came up with this feature detection with scale selection theory. This is an important theory, scale selection. We want to extract features with a characteristic scale that is covariant with the image transformation. So what you saw was Harris corners are not scale invariant or scale covariant. So therefore, what we want to do is extract these features in a manner that are covariant with the image transformation. Yeah. So notice this. Now, if you have a function that responds to this uh, blobness, let's say blobness, and for this image it has responded the highest at 10.1 scale. For this image, it has responded the highest at 3.89 scale. Now, can you see, because this sort of scale is there, if that corresponds to the radius of this detection, our problem is solved. If we can find the so-called characteristic scale that maximizes some function, our blob detection problem is solved. Yes. So when our scale detection function gives a maximum response, we take that as the correct scale. It's a beautiful theory. Okay. So now you can see to detect blobs, we convolve the image with a blob filter. This is called a blob filter. At multiple scales and look for extrema of filter response in the resulting scale space. See that the way you do that, you convolve the image with, convolve means you know that you run the filter at multiple scales and pick the scale that maximizes the response, as I showed you in the previous diagram. Now this is the kernel that you have to run. So we will study about this kernel a little bit, and then we'll be able to see. So now watch this. So now find the maxima and minima of blob filter response in scale space. Now this is the so-called blob filter. So now you can see inside it's dark, right? This is dark. And there is a bright annular shade. And then this is very dark plus or something. Then outside it's dark, right? That's what you see here, right? Very dark, bright, little dark. That's the nature of this blob filter. So we know that when you filter, the filters look for things that look like itself. So therefore, if you have something like a black dot, for example, this is a black dot in sort of white background, the filter has given you the maximum response. But in this case, are going further, the filter gives a maximum response if the scale of the blob size matches with the structure of the image's size at that location. Yeah. So because we are doing at different scales of this blob, at some scale, it will maximize. We want to find what that scale that results in the maximum value is at every single uh, location of interest. So that you can see the maxima and the minima in this one. Okay. So this is that Laplacian or Gaussian blob filter. It is a very easy function. So we know what this G is, right? The Gaussian. Do you remember what G is? G is equal to, I can remember. If you take G, it is a function of xy, of course. 1 over 2 pi sigma squared I hope you can remember e to the power of minus x squared plus y squared divided by 2 sigma square. I hope you can remember that. So what is this? You take that Gaussian here and you differentiate it twice with respect to x. Yeah. And then you differentiate it twice with respect to y. That's all. And then we have this so-called Laplacian operator. Okay, we call this Laplacian of the Gaussian. So Laplacian operator is this one. Twice differentiating operate in either direction. Yeah. Okay. So in the H direction, if you recall, we looked at this in the morning. Also today, you have the image, noisy image, and you have d by dx g. If you get the derivative of the Gaussian, and you convolve the image with the derivative of the Gaussian. So here you can see you will get a peak here. But in this case, we have d squared by dx squared g. Why do you have, why can you put d here? You can put d here because this is one dimensional. Then partial, you don't have to consider the partial derivative. You can just consider derivative. Then if you convolve the image with the derivative of Gaussian, the second derivative of the Gaussian, which looks like this, at the edge, what will happen? You can think about it. What happens here? By the way, this shape shall be justified. Now let's take the Gaussian. In 1D, the Gaussian looks like this. If you differentiate the Gaussian, there will be zero derivative here, maximum derivative here, maximum positive, some derivative here, some derivative here, zero derivative here, it's a horizontal line, little bit negative, maximum negative, little bit negative, zero. So if I plot that, 0 and goes to the maximum here, goes to 0 here, and goes to negative there, and goes to 0. This is the derivative of Gaussian. This is g, this is d by dxt. Right? Now, d squared by dxg means what? D squared by dx squared g means what? You have to differentiate this again. So here, if you look at this, here derivative is 0. Here some large value. Here is 0. Here negative large value, negative, negative, negative. Then negative small values, negative small values. Okay. 0, positive value, 0. So with this, if you draw it, you can see that starting from 0, let me use a different color. Starting from 0, it goes to positive, becomes 0, and goes to a very large negative value, becomes 0, a bit positive, and can you see? This is that one. So when you run this, at the edge, it will give a 0 value. Just before the edge, it will give you a maximum value. Just after that, it will give a negative value. So edges are detected as zero crossings if you run the Laplacian or Gaussian operator. Actually, this is the 1D case, and you have to run that in 2D. Okay. Okay, now comes the important part. Huh? Okay, I hope you are paying attention. If you have any question, I'll let you ask, please. If you did not understand anything, please don't hesitate. Okay. All right, watcha. Now, we know from the previous one, now if this is a one-dimensional image, now here you can see in this one-dimensional image, there is an edge here. There's an edge here in this one-dimensional image. So from the previous slide, we know at edge, this derivative of Laplacian of Gaussian filter will give you a zero crossing. At the edge, zero crossing. So you can see at the location corresponding to the edge, this particular location, you have zero crossing. Here also you have zero crossing in the response of the Laplacian of Gaussian filter. Now what we do is we shrink this filter, shrink this image, shrink this image. Actually, by shrinking, you know that what we are doing is sort of if you consider this as uh, a circle in 2D, okay, 2D in circle or something, we are controlling the radius of that, right? So you're shrinking it. When you shrink it, these two blips come closer. And you further shrink it, they come even closer. If you shrink up to some extent, some number, they will merge. The two blips will merge. Merge. Now this size of the radius here, this radius of that blob matches with the corresponding sigma value that we use to construct this Laplacian of Gaussian. Yeah. Okay. This produces the maximum value. So spatial selection means the magnitude of the Laplacian response will achieve a maximum at the center of the blob, provided the scale of the Laplacian is matched to the scale of the blob. Okay, so we want to find the characteristic scale of the blob by convolving it with Laplacians at several scales and looking for the maximum response. However, the Laplacian response decays as the scale increases. So unfortunately, when sigma increases, the value of the Laplacian decreases. So although you have the sort of blobs merged, these blips merged, you cannot detect it because it's so small, so small. So therefore, you have to do so-called normalization because this normalization factor is there. So the response to the derivative of the Gaussian filter to a perfect step edge decreases as sigma increases. To keep the response the same scale invariant, we must multiply the Gaussian derivative by sigma. Laplacian is the second derivative, second Gaussian derivative, so it must be multiplied by sigma squared. So therefore, if you multiply sigma squared, you will get the maximum response as we wish when the sigma matches with the image size, the blob size in the image. Okay, that is a maximum. So therefore, the scale normalized version of the Laplacian or Gaussian is multiplied by sigma squared. Okay, so this is a circularly symmetric operator of the blob detection. This is the operator. Which we see now, although it appears very logical or simple to us, when people want to discover these things, I think they spend quite a bit of time to understand these things. Okay, now this in there in the quiz also, it is important to understand what I just alluded to. I just said that, but without going through mathematical reasoning, how to relate the sigma of the this Laplacian of Gaussian. To create that, we use a sigma for the Gaussian, and that how that sigma is related to the radius of the blob that gives a maximum response to that Laplacian of Gaussian kernel. Again, what is the radius of the blob that gives you the maximum response to the Laplacian of Gaussian particular sigma? That's the question we asked. At what scale? So when you say scale, we are calling the scale synonymous with sigma. Does a Laplacian achieve a maximum response to a binary circle of radius r? So this is a binary circle because we have drawn that with white and just black. That's a binary circle. Okay. So now the to get the maximum response, the zeros of the Laplacian have to be aligned with the circle. So you can see in the Laplacian, in the red one zero is here, zero crossing, another zero crossing there. So you can see the image of the circle. So now if you get a cross section of that one, you will get bright to dark to bright transition, right? So if you draw a one-dimensional map of that, what you will see is this kind of a well kind of a thing. Yeah. So that is what we are representing here. So the zero crossings of the Laplacian must align with those image edges, with this one and that one. So using this, we can derive a relationship between sigma and r. Okay, let me clear the sketches. Okay, the Laplacian is given up to scale by x squared plus y squared minus 2 sigma squared e to the power of minus x squared plus y squared plus divided by 2 sigma squared. I can prove this, but I will not prove it right now. Now you can prove it by computing the first derivative of the Gaussian, second derivative of the Gaussian, and adding it and making it zero, because we are considering the zero level set. Okay, so therefore the maximum response occurs at this value. Sigma equals r divided by square root of 2. I hope this is clear to you. Okay, I can derive it, but I will not derive that now. You have to compute the two derivatives and add them. No big deal actually. Okay. So this was by people by Coinderink and Tony Lindeberg. I have read parts of his book also. We define the characteristic scale of a blob as a scale that produces peak of Laplacian response in the blob center. Characteristic scale. So how do you do this in summary? Convolve the image with scale normalized Laplacian at several scales. So here you can see with a very small blob, little bit large blob, larger. So you can see larger and larger structures appear. And after that, you align them in a sort of vertical axis. And if at every single pixel, you get the local, with its consider with its a local maximum. So there is a little bit of an algorithm there. So after that, when you detect these blobs, you can draw circles because you know the radius also. You can draw them. So this is how I have drawn some of these things. Maybe I'll show you a code. Uh, Before that, I will point you to the model because now I have put all the code files in slightly proper arranged way. So images are here, code files are in this folder. So you can see I have constructed, I have given the HTML format also because then you can quickly see them. The introduction class that we did and the image processing basics. So I broke the file into two now, and then intensity transformation what we did and spatial filtering what we did. So since the HTML files are there, you can just download them and see. They are easy to see. So uh, having said that, I will show you a bit of code uh, for this one. So all these things that I discussed in the lecture, I have coded them for you to see. Please run them and see. And then generation of the derivative Gaussian filter, Harris corners, Kenny edges, all these things. I have coded or found code from different places and connected them. Okay, so here is the blob thing. Okay, uh, uh, can you just take a minute to briefly understand that? I will be back. Take a minute to understand that what we have done here. So what you want to do is to relate this with the slide. So uh, I hope you can hear me here. Oh, so this is the Laplacian of Gaussian that we checked, right? So let's try to relate them. Maybe let's try to display both of them. Okay. So, of course, you have xy that represents the spatial coordinates using which you can compute this. 1 over 2 pi sigma squared. So the scaling, I have written x squared divided by sigma squared, y squared divided by sigma squared minus 2 e to the power of x minus x squared plus y squared divided by 2 sigma squared, which is exactly this. So you can see this part e to the power of minus x squared plus y squared divided by 2 sigma squared. I have exactly written that. And this is x squared plus y squared minus 2 sigma squared. Okay, I have divided by sigma squared there, so you can see it is the same, almost it's the same thing mathematically. I have divided the whole thing by sigma squared, you can see. And then I have there's some scaling factor also in front. I don't know why I decided to do that. I have done that, so it just doesn't matter, right? So when you display it, you can see the Laplacian or Gaussian. You can see that nature, right? Center dark and then bright and then grayish thing. So I have displayed that in 3D also, so you can see it in 3D. It's a beautiful picture, right? Beautiful, beautiful. It sort of represents what happens in life also, right? Sometimes, assuming that you are in a place like this and you are safe, and you want to do maybe too much extravagant things that are not good for life. Maybe you want to drink too much alcohol or something, have smoked too much or something, then you go to the very edge of life, right? And then if you fall, there's no coming back. So it's like related to what happens in life also. Okay, so I hope that code part is clear for you. Then then what I did was I wanted to uh, experiment with that scale selection filter. That means, oh, if I'm given a block, can I find out its scale as the radius? Sigma times square root of 2. That one. So this is yeah. So sigma times square root of 2 is the radius. I'm trying to see whether I can do that, but to do that, what I have done is I have created an image of radius 14. So you can see it's a sort of 14. You can see sort of 14. And so I have created that. I have created that by doing some jugglery here. So you can see this one on your own. I will not spend time on that. Then what I did was I created a lot of Laplacians of Gaussian. I created one here, one of them here, and I explained you the code briefly for this one. And then I created, now here, there you can see sigma is equal to 10. And I have selected half with tri sigma and so on. All these things I've done properly. Then what I did was I created a whole lot of them. That means I have sigma values going from 5, 6, 7, 8 up until 15. So all the values of sigmas 5, 6, 7, 8, 9, 10 up until 15, I have created Laplacians of Gaussians. Beautiful, right? I mean, these are beautiful. If you are young and you show it to your mother or someone, your mother will think, okay, I bought this person a laptop, he's putting the laptop to proper use or something. And if you are married and you have a wife and who was against you buying the laptop computer because she thought that you're buying this laptop computer to browse Facebook all the time or something, now you can show that you can do some beautiful computations with this laptop. So I encourage you to uh, look at these codes and please run them and run on your own. Also, these are small pieces of code you can see, few lines, but theoretically very important. So Laplacian or Gaussian. So I have written. Then what I did was I took this Laplacian or Gaussian and convolved the original image with that. Convolve the original image with the original image is a little bit large, but I've convolved them with that. And then you can see the different kinds of responses. I don't know where the highest response comes. I think maybe I'm thinking the highest response may be somewhere here. So which I found. See, highest response comes at the center, 35, 35. Um, yeah. Then R is the square root of 2 times sigma. Yeah, so sigma value is 10. Because sigma value is 10, I can, if I multiply by square root of 2, square root of 2 is equal to 1.414. I gets as a radius 14. So there you can see that's the original one that we had when we created the image. So multiply sigma by 414. So when I draw it, the red circle, you can see it exactly matches with the radius. So it's a beautiful theory. As you can see, any questions on this scale selection or blob detection theory? We can derive this equation, but I do not want to do it now. This derivation. Maybe you can use ChatGPT to derive it. But I will maybe show you how to do that. Yeah, what you are implementing is this one. And setting it equal to 0 to find the zero crossing the radius. So because of this thing. Yeah. Let's get started then how to just do that. Okay, we have gxy equals 1 over 2 pi sigma squared e to the power minus x squared plus y squared divided by 2 sigma squared. Then different now what we want to get is this one. I want to get partial derivative, second partial derivative of g. And I want to compute this one first. To compute dabba squared g by dabba x squared, I had to compute dabba g by dabba x, right? So let's compute that first. So we just call g here, dabba g by dabba x. Differentiate with respect to x. So 1 over 2 pi sigma squared is there. It's a constant. How to differentiate e to the power of something? So d by dx, e to the power of x is e to the power of x. Rules from your O level, A levels. D by dx, e to the power of ax. A to the power of x. Uh, then finally d by dx. If you have something like e to the power of ax squared or something, what do you do? What do you get? Ax squared e to the power of x. Then d by dx, ax squared, right? E by dx x squared. This is what you have. So if you differentiate this, you will get minus x squared plus y squared divided by 2 sigma squared. then the derivative with respect to x of that times 2x minus 2x. Here, I forgot the a, right? So you can see that now you after that you have to get d dabba squared g by dabba x squared. Then you have to similarly get dabba g by dabba y. By symmetry, you can get that without a problem. And dabba squared by g by dabba y squared. And this you have to just add and equate it to 0. Then you will get this formula. This one. Okay. So I hope this blob detection is clear. So here you can see the blobs have been drawn. The radius, of course, you know, that is r. Each of these r's is equal to 2 square root of 2 sigma of that corresponding sigma. Corresponding sigma. So different locations will have different sigma values resulting in the maximum. Now, if you wish, you can use this to detect coins. So I have some coin images if you like. This is called a cent. This is 1 cent coin. This is 5 cents, 10 cents, and a quarter. So these are called quarters, dimes, nickels, and pennies. If you're given standard 300 at canvas, you can task to detect coins and tell me the amount of money represented in the images. Then tell me the assumptions. So you can use template matching, normalized cross correlation, blob detection, or different things can be done. If you like, you can do that. I can give you these coins. Sample. Okay. Any questions up to now? Okay. So now let's move forward. Now this approximating the Laplacian with the central difference, with difference of Gaussians. Sorry, the Laplacian computation, you can see the second derivative of the Gaussian, and multiplied by sigma square. That's a Laplacian. So it's slightly expensive. You can do that, but this one is less expensive. Difference of Gaussian. So there, what you do is you compute just the Gaussians with a particular sigma value, k sigma, and another sigma value. These values are close, k sigma and sigma close by sigma values, and you get the difference between them. When you just minus, you get a similar behavior to this function. So you can see this graph shows the Laplacian and the difference of Gaussian. They are almost the same. So because of this similarity, you can use difference of Gaussian instead of the Laplacian of Gaussian. This is what in this one of the most famous papers in computer vision by David Lowe, distinctive image features from feature scale invariant feature key points. This is called the SIFT paper. He did. So he had the Gaussian convolved image. These are the Gaussian convolved images. He subtracted the adjacent ones, and he got the difference of Gaussian. So doing the extrema detection in Laplacian of Gaussian planes is the same as doing the extrema detection in differential Gaussian planes. But one thing is when the scale, the Gaussian sigma value becomes larger and larger, it is not necessary to keep this kind of image resolution. This is like large image, so you can halve the resolution. So these kind of tricks also they did in their paper. Okay. So from feature detection trick now we know how to detect some blob in an image, and we know how to find the scale of that blob as a sigma value. That's beautiful, right? Now, what we want to do is, now detection is fine, but how do you match them? How do you match them? So you have to match, you have to represent each of these blobs with a signature. Signature. This signature we call a descriptor. So scale and rotated versions of the same neighborhood will give rise to blobs that are related by the same transformation. That's fine. What to do if you want to compare the appearance of these image regions? Normalization, transform the regions into same size circles. Problem is the rotation ambiguity. So if we take two blobs, these are not exactly these one, some things. So now you have put them in the same scale, but you can see the edges in this one are like that. This one are like this. So there's obviously a rotation problem here. So to assign a unique orientation to circular image windows, this David Doe's paper created a histogram of local gradients in each patch. So let's try to decompose that. So here you can see, now this is think that this is the that radius of the block. Let's think about that like that. Maybe it's a ratio of that. Then you divide that into this many small rectangles. This many small rectangles. In those rectangles, you compute the amount of gradient it has. So here the gradient is this way. Here the gradient is that way, and so on. Okay, so many gradients are now there because we are computing the gradients in these patches. Why is a gradient an arrow? Because it is a vector, a partial derivative in x direction, partial derivative in y direction. So therefore it's a vector. We saw that in the morning. So then we synthesize that into a histogram. What that means is, if you find a gradient in the horizontal direction, this one, this one, this one, this one, you put them in the 0 to is 22.5 degrees. Degrees one, this 45 degrees. So you have divided this set of angles, possible angles to slots of 22.5 degrees, 22.5, 45, and so on. And then you put these numbers, gradient strengths added to this bin. So those that are between 22.5 and 45, you put into that bin, and so on. Now you can see, we can find the dominant gradient direction by picking the maximum. So the maximum, corresponding value to the maximum is, you can see between 22.5 and 45. You can add them and divide and get a number. So you can see the dominant gradient direction sort of gives a orientation, rotation of the blob. So that's the dominant gradient direction, you can see. And that therefore, in the SIFT paper, you can not only draw the sizes of those blobs by rectangle or circles, but you can draw an arrow representing the direction of that. Okay, so with this, these are descriptors. Now, with this, we can match detection is covariant, feature transform image, transform feature image. So this kind of thing is okay. You transform an image using rotation or something and compute feature. This is fine because we have understood that. Description is invariant to the features because for if you take this kind of a uh, blob or this kind of a blob, yeah, they must give rise to the same feature descriptor. So this is what you can do by this aligning the orientation. So now how do you exactly compute that descriptor? Here is how they do that in the paper. So here once again you can see that circle, and then you have divided that into grids. So in each of these cells, you have small gradients in different directions. So they synthesize them into 8 directions. That means in the horizontal direction, how much is the gradient in this block? In the vertical direction, in the northeast direction, how much? In the vertical direction, how much? And like that. So therefore, you can draw these 8 arrow things in each of these location centers of these blocks. How many numbers are there here? 8 numbers. How many numbers here? 8. How many numbers here? 8. So altogether, 8 times 16 numbers, right? How much is 8 times 16? 128. 128. So this is the size of the shift descriptor. 128 numbers. So this is a beautiful contribution. So you can see now these two images, this couple has now, this is the background. It's the same background, but you can see it's an entirely different image. But the same features have been located, same feature descriptors. Can you see that? Same. They are the same. So irrespective of changes in, this maybe is wrong, right? Changes in viewing angle, illumination, this, that, and so on, shift feature descriptors are invariant, those. Extraordinarily robust detection and description technique can handle changes in viewpoint up to about 60 degrees of out of plane rotation, can handle significant changes in illumination. You can, as you can see, fast and efficient to compute, can run in real time, lots of code available. But this is a patented technology. Yeah. Yes. So, but I will be, before this, I will show you a deep learning based one. Uh, this like the two deep learning based ones are there. One is called Colmap. If you take a Colmap, so Colmap is a general purpose structure for motion. Okay, one by pipeline with graphical and command line interface. It offers wide range of features for reconstruction of ordered and unordered image and software line, whatever. I think it allows you to use the SIP features. Select features. Yeah, you can do that on your own. So because I did not do it at home, so I don't want to keep on clicking places. So you can see Colman. And then there's one called Super Glue. So this one is an extremely fast feature detector and matcher using deep learning. You can see how fast these are. So there may be better ones. So if you want to match between features, I think it's good to use SuperGlue. But SuperGlue training code is not available. Only the inference one is available. You cannot change it though because of that. Okay, so let's briefly talk about the affine adaptation also. Now all those shift points are shift features and shift descriptors are invariant to rotation. That means to up to some extent the camera viewpoint, they are not fully invariant to affine changes. That means um, this is we are talking here. We are talking about affine changes in the image, not the intensity. So you can see this eye or the circle has changed into an ellipse, right? This kind of change. This kind of change. So due to camera, these kind of things happen. So we will deeply study these things later. A circle can become an ellipse. So these kind of viewpoint invariants can be handled by set features. So therefore, you can do some adaptation. See, affine transformation approximates viewpoint changes for roughly plane objects and roughly orthographic cameras. So then there's this thing called affine adaptation. Consider second movement matrix of the window containing the blob. And then we recall this how the eigenvalues are related to that. This ellipse visualizes the characteristic shape of the window So this is the scale invariant blobs. These are fine invariant blobs. You can see that they have become ellipses. So it is much better, right? Yeah. Yes. Okay. That's all we want to do about features. I want to show you a brief code in getting the SIG features matched. So these are the SIG feature matching code. So you can see finally, as I showed you in the column, you can get the features matched across two images. Later on, we will use that to make a small 3D reconstruction called structure from motion, but not as extravagant as you think. It will not look nice. So you read the two images. So these are called graffiti images. I'm reading the graffiti images. I can give you those images. Let me know. Uh, hmm. After reading the graffiti images, you sort of say shift.create, so to create that object. And from that, you detect and compute in image one. In the image one, you compute key points and the descriptors. So now you understand what key points are, right? Those are locations of the image with the scale. Location and the scale, both are there. X, Y, and the scale, key points. And then you can get the descriptors attached to those points. So you know what this descriptor is, 128 numbers. At each of these points, there will be a 128 number, 120 dimensional number. And you do that for the second image also. All right. So now after you do that, you do a couple of things to match them. So they have the so-called plan-based matcher. You should not write the matching code on your own. And then after you do that, there are some little bit of juggleries to do. So please look at those things in the code, and you can draw these lines to match, show the matches. So there are obviously there are incorrect matches. So from starting the next lesson, we will see how to get rid of these incorrect things that happen in these things. So that is called fitting. So we will look at that in the next. Okay, I will have you look at this code a little bit. So once again, I have uploaded these code files in this one. So you can see spatial filtering is there. Oh, okay. Today's one I didn't upload, so I will upload that. It is corners and blobs. I want to upload both the HTML version also so that you can easily see this. So if you look at this HTML file, you can download it and see without using any code. Read it. So these matches, okay, in base matching, yeah, after matching, you can take those matches and see this whether this some kind of distance short kind of a thing is there. So we had to spend a little bit of time to understand that. Then you mark the matches and then you draw the lines between those matches. Okay. Uh, to summarize what we did briefly, now you can see we understood how to detect edges. That's fine. Then we understood how to detect corners using the Harris corner algorithm. Uh, Although you detected corners using the Harris corner algorithm, you realize that this Harris corner algorithm let me write that down. So We did edges. Good. Have good handle of this writing pad. We detected edges. And secondly, we realized that using these edges, we can get single lines. That is our canny edge detector. And as a third one, we detected corners. And for that we had the second moment matrix. Second moment matrix, and then it gave rise to the Harris corner detector. Then we realized this Harris corner detector is invariant to a fine illumination changes like AI plus B. That's okay. Rotation. That's okay. But we had a scale problem. Covariant, partial covariant problem scale. So to handle that and to find the characteristic scale, we looked at blob detection. So actually this is scale space theory. There's a thing called scale space theory. And we were able to relate our R and the sigma. So, but this is fine. But detecting blobs and scale is good. Because after that, for every location in the image that show this max extrema, let's say these are those locations, I can get the x coordinate, the y coordinate, and the scale sigma. X2, sorry, x2, y2, sigma 2. Like that, we can get these key points. These are called key points. Key points. But key points do not allow you to match them. To match them, you need a descriptor. Then we understood how to compute the set descriptor. Set descriptor. And it's a 120 dimensional one. So at each of those key points, we will have one of those 120.8 descriptors assigned. With this one, we can have an image, and we can have another image like that. And between the images, we can match these points. This matching is possible. Right? Point matching is possible. So with this matching, perhaps you can do a 3D reconstruction. Perhaps you can detect objects, and all these things are possible. Yeah, I hope these are sort of clear to you. Any questions about this? Some quiz questions are also there. You can look at the quiz questions. Yeah, so now you can see, if you look at the code again with that light, in summary, so you have the first image, image 1, second image 2, then you create the so-called shift detector. This is the object that we create. Our known detection is done, and then detect and compute. Both the steps are done here. So you can see key point 1 and descriptor 1. Key point 1 means the key points in the first image, and descriptor 1 are the associated descriptors in the first image. and key point 2, the key points in the second image, descriptors in the second image. So if you look at one of these things like KP1, all of them will be there. We just print it and see. So you can see CV key point. Okay. Now we need to get that. I don't know how to do that. So I'll ask ChatGPT how to do that. This way, it's good to use ChatGPT because you know exactly what you want to do and you just need some here. So see, uh, this is the way it seems. So let's run that. No, this is I think better. Okay, let's run this. So you can see key point 0 coordinates are there. You can see these coordinates are subpixel accurate coordinates. Pixel 2, 320, not like that, 2.4 whatever, and because they have some function in the SIFT paper how to get these subpixel accurate things. And the size, that's a sigma, right? And the angle orientation is there. All other things are also there. So again, different ones. And so many of them. So many of those ones will be there. So many of them. So this IJCB paper, this is the famous David Lowe's paper. You can see the diagrams that we had in the slides are there in that one. You can see the difference of Gaussian computation and how they get the local maximum and so how they made some decisions. They are there. And then how they compute the descriptor and other things that they do after that. And there are applications also, for example, matching objects like that. They have shown those applications in their paper. Matching these totem poles. Yes, that's a great contribution to computer vision. So if you take Google Scholar and search for David Lowe, you can see massive number of citations for that person. So you can see for the SIFT paper, 79,000 citations, 80,000 citations. Our whole university does not have this many citations. Okay, so that's what I wanted to cover in the first part of the lesson. So I uh, we can take a break now and we can meet at 12. Well, 15. So please do the quiz if you do not have anything to eat or something. I'm very sorry about that. Otherwise, you can have a snack or eat anything. But before that, do you have any questions? Please type questions if you have any questions. You can see slightly the lessons are getting slightly difficult. That's a nature. So now you will have to pay attention and write these pieces of code on your own. Okay, then if you don't have any questions, I will post the recording. Hello, good afternoon, everyone. I hope everyone had a break. Now we want to look at the new topic of fitting. Now, we have been studying about how to detect canny edges and how to detect corners and how to detect blobs and so on. Now that we have these basic structures, what we want to do is fit slightly high level things to those. For example, assume that we have canny edges like that, the white edges. We want to fit straight lines to those. How do you fit that? This is the question we are asking in this fitting lesson. In this, we will understand how to fit a line by using the least squares line fitting, which you already we know. And then we will look at the total squares line fitting to solve some problem in the least squares line fitting in the image processing context. Then there are other ways of fitting things like using the half lines, half circles, generalized half transforms. We will look at them. And we will realize some problems due to outliers in line fitting. And to reduce those, we will learn a technique called to get rid of those. We will learn a technique called ransack. It's a very, very powerful technique. So this is the plan for this lesson. And I have all the code which I have uploaded. Okay. So we learned how to detect edges, corners, and blobs, and now what? We would like to form a high-level, more compact representation of the features in the image by grouping multiple features according to a simple model. Choose a parametric model to represent set of features. For example, we can represent lines. So lines, can be parameterized using the gradient and the intercept, those A, B, C, those three parameters. And we can fit circles, center, and the radius. And we can have slightly more complicated models fitted to a car or something. Yeah. But this is a very challenging one. If you want to detect red to white transition lines here, you can see that these lines are also there. It's a very difficult exercise usually. Noise in the measured feature locations, extraneous data, clutter, outliers, multiple lines, missing data, occlusions, all these problems are there. Yes. So this is the agenda for this lesson: least squares line fitting, robust line fitting, ransack half transforms, generalized half transforms. Okay. Now least squares line fitting. But before I go through this about the quizzes, so there are quizzes. I'm sure that some of you are not able to do it today due to the long weekend or something. It does not matter too much because if I give 10 quizzes, I will take the best 8 out of that. So that means even if you miss 2 quizzes, you can get the uh, full marks for the quizzes. Okay. Yes. So now assume that we have data points x1, y1, x2, y2, xn, yn, and so on. I have plotted one data point here, xi, yi. So you can see the other data points there. So these things we know correspond to a line, straight line. So we assume that this straight line's equation is y equals mx plus b. Yeah, this is the gradient, this is the intercept, and we know that. So what we want to do is to find m and b in such a manner that we minimize this error this distance between the actual point and the line that we came up with, this distance, summation of all these square distances. Now you can see why it's called least squares line fitting. We fit a line so that the squares are minimized. So you can see exactly now if you take this point, it is xi, yi, its y coordinate is yi. Now, if my line is there, what does my line, assuming that we have M and B, okay, we don't have them yet, but assuming that we have, what is the y that it predicts? Now, this location is xi, right? Xi. So this line, this one will predict M xi plus B, assuming that we know M and B. So there is an error between yi and this one. That is written here. Very simple, right? Now, we looked at it for only one point. There are n such points. So therefore, we sum these squares over these n points. So if you can minimize this function with respect to m and b, we find the optimum n and b in the least square sense. I hope that objective is clear. Then how do you go about doing that? Now, this we can write as, of course, in terms of matrices, which we always do. Now, let's see whether this is correct. Now, if you take one of these equations, you can see, oh, all right. So, um, let's consider this one. Just to show you that this is okay. This equivalent thing will look so. In this, if you take the first row, x1 multiplies m, 1 multiplies b. So you can say what has been written is correct, right? And then y1 is at the right-hand side and the signs are different, right? It is sort of okay. But we have not proven that finding the least square solution to this is the correct thing. But that is okay. So let's call this capital X, this matrix, all this capital B, this matrix, and all this capital Y. So what you want to do is this is given by this equation. This one is called a pseudo-inverse. Pseudo-inverse because this may not be a square matrix. Not maybe, it's not a square matrix. Okay, solution is given by this one. Okay. It's a very simple solution. If you want to prove it, you can prove that by differentiating with this with respect to m and differentiating with this with respect to b. But I will not do that right now. You can do it, but take this as a solution. Okay. So I will show the implementation of that. Okay. So this is the equation, as you remember, x transpose x inverse x transpose y. Now, let's see how I have done that. So I have taken m equals 2 And actually, this is B, right? C equals 1. Maybe I can convert that to B. And then what I did was I got some random noise of the size X, and I have some O or zeros with respect to these for the outliers actually. And then I computed y equals mx plus b plus n for 10 such numbers of x, 10 such numbers of x. X is from 1 to 9, right? 1 to 10, 1 to 9. Let's check that later. Then one thing is this x has to be constructed, right? We saw that x is actually the x column plus a column of ones. So you can see NP concatenate, that is how you put things together. The x reshaped and ones, column of ones. Now that's done, capital X is there. If you print capital X transpose X, you will see that matrix. And I get the pseudo inverse, X transpose X pseudo inverse, multiply by X transpose and multiply by Y. You can see this is the expression. So I call them M star and C star, the true solutions. Then I do some plotting. Mhm. So we can see this is X transpose X. I have printed that. And pseudo inverse we use and we calculate B. And I have printed B. B has two numbers, the intercept and the gradient and the intercept. What I have used are 2 and 1. You can see that you have not gotten those things because of the noise. So you can see the original line is the black one, and the points are these, the blue ones, and the estimated line is in red. If you increase the noise, this will become horrible. But if you increase, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Because I have put 1 to 10 here. So let's put about 100 points. That one. Now you can see you get exactly almost the same values, right? Because you have so many points. 2 and 9, 4. Yeah, I pick 2 and 1. But you can see the problem here. When small number of points are there, it seriously get affected by noise. But generally okay. Any questions about this? Is that okay? Okay. Then let's move forward. I hope you understand that. And then let's discuss the problem that this method has. Is this a good solution? Slope intercept parameterization fails for vertical lines. That's a problem with this. So for lines like this, these are the points, okay? These are the points. But if you have a line like this, these are the points. Now, the line will be like that, no? To that line, we can compute the error distances without a problem. But if the line is vertical, how do you compute the errors? Because you cannot vertically compute the error, right? There's a big problem. Because we compute the errors as the y difference. Y minus yi, right? Predicted value minus the given value. But here you cannot do that. It simply fails. So this is the problem with this one. Solution is not equivariant to rotation. So if you have an image, assume that your image is like that. Okay, if I rotate that image like this, then you have a problem. What you were able to compute in this image, you cannot compute in this image. There is a problem with this least squares line fitting. So therefore, we go for a different parameterization. Rather than computing the vertical error, we compute the error perpendicular to the estimated line. So now you can see these are the perpendicular distances. But we need a little bit of theory to find the distance from a point to a line, perpendicular distance from a point to a line, right? And also we use a different parameterization of the line. In this case, our parameterization will be ax plus by equals d by parameterization, like this one. You can see that. And we had to know from theory, AB is a unit normal to the line. That is a square plus b squared is also 1. Is a normal to the line. So d is the distance between the line and the origin. So those are theories from this representation of the line. Perpendicular distance between point xi, yi and line ax plus by plus d, assume a squared is equal to plus b squared is equal to 1 is this line. This is the distance. So that distance we have to square, sum and minimize. So solution is of this is the objective function. Now axi plus bi minus d squared. This has to be minimized. So solve for d first. You did get the partial derivative with respect to d. So you can see it is this is a summation from 1 to n. That's okay. So if you take individually each of these terms, each term will contribute because this square is there. So you get 2 times the same thing. And d's derivative is 1. So you just multiply it by 1, right? This has to be set to 0. If you do that, you can get the summation of each of these elements, a over n xi, b over n yi, and then you sum d how many times? N times. So therefore, you have that divided by n. So this is actually the averaging of xi's and averaging of yi's. That's why we call it xi bar and y bar. These are the averages. Mean value. Average of the mean value. Mean values. Okay. Now we plug that back in. So we have formula for D. We put that back in here. So then you have A xi minus x bar, B yi minus y bar. So this is the one that we have to minimize. So we write that in matrix form. That's I think you can see it's correct. We call it U matrix and N matrix. We want to find N that minimizes UN square subject to N squared equals 1. So why is this minimization is there? You have to minimize. Why must N squared be equal to 1? Otherwise, if this N becomes, you can make N 0 and make this total value 0, right? 0, 0. So we should not let that happen. Then there's no unit normal, right? I mean, that does not properly represent a line when both A and B are 0. So that should not be correct. So therefore, we have to set this constraint of n squared equals 1, norm of n squared is equal to 1. That constraint is very important, this constraint. Okay, but this is hard to solve if you do not know how to solve it. If you know how to solve it, it's one couple of lines. The solution here is a solution. Solution is given by the eigenvector of U transpose U associated with the smallest eigenvalue. Solution is given by the eigenvector of U transpose U associated with the smallest eigenvalue. So that means you have to construct U transpose U, compute its single value decomposition, and we have to pick the vector that corresponds to the smallest eigenvalue. Yeah. Okay, so these U. I hope you can agree with that. And then this is U transpose U. I think actually, although I have written that, in reality, you don't have to calculate it like that, right? Because you use Python. You try to use transpose U. And it's called second mode matrix also. Here's a pictorial view of what we discussed. So you can see we said that the d is the distance to this line that we want to compute, this line that we want to compute. And we said that the n equals AB is the unit normal. And then if you take the mean of that, this is x bar, y bar. And if you take a particular point, this is the difference between xi minus x bar, yi minus y bar. So you can see this is the pictorial view of that. So now I will show you the code of how it's done. Total least squares. This is called total least squares. So it's a slightly a very small piece of code, but it's slightly mathematical. Again, you can see I have picked whatever n equals 100 MC. So let's call this B. B. Once again, I am creating the points as by adding random noise. So the scale of the noise is S. Then plotting the scatter. Here's the ground truth line. Then D is equal to AX bar, BY bar, and U, yeah, this is minimize U n square subject to n squared equals to 1. Totally square, so capital N is there, X underscore, so X line, we call it. U is X underscore minus mean, subtract the mean of that from that. So then you get this matrix. Then to compute the eigenvector of U transpose U associated with the smallest eigenvalue, you get linear algebra single value decomposition of NP U transpose U, U transpose U. And then the smallest corresponding smallest eigenvalue, so you have to pick the last row of that, and you get the 0th element as A, element number 1 as B. Then you can compute D as A times mean, B times mean of X and Y. So this is the formula for that. Then base model of the line is there, so then you can plot it and see. So here I have plotted that. You can see all points are there. Total least squares line is there. Ground truth line is also there. I don't know whether this ground truth line is correct. There's something wrong in that. This is the ground truth line. something wrong. Because there's something wrong. Some offset is there. Decomputation is wrong, I think. So underscore plus B. Mm. I cannot find what the problem is. I mean, it's just a plotting problem. Here it plotted properly. Are we manipulating M somewhere? I'm sorry, I cannot find it. So the round truth line is a offset. That's maybe I'll find it later. So this error is okay. Okay, now let's look at the effect of noise. Now, least square, so whatever. Um, total least square, so least squares. If you have noise, it seriously gets affected. You can see here, not noise, outlier. So here, this one, I put an outlier. The last element I put as 20. So you can see it's an outlier. So you can see the original line, the estimated line totally gets dragged by that one outlier. So this is the problem in these things. They are very sensitive to outliers. I'll show you that. Now, this set of points and the optimum line is drawn. If you have an outlier, the optimum line drastically rotates. The problem with the squared error heavily penalizes outliers. So you can see the error between this and this is like 0.1 or something. Error between, if you take this line, assume that we are able to get the correct line or something. Assuming that the correct line, we somehow estimated the correct line. Assuming that we somehow estimated the correct line. So error between this point and that line is very small. Error between this point and that line is huge if you take the least squares. This is a huge number. But in the new line, the incorrect line, that error is this much. This error is also that much. But it doesn't matter if this is like 1 and this is like 10. You can see 1 squared is 1. But 10 squared is 100. So what dominates this optimization is this large error. That is a problem when you have an outlier. So therefore, what we want to do is when the error gets large, you curtail that by using a so-called robust estimator. A robust estimator. There you can see rather than computing the residual or the error, we go through a robustifying function. This robustifying function, now if your error is um, in the earlier case like 0.1, you apply this much of penalty, error squared. If your error is large, you apply a massive penalty. You cannot even show it in this graph. That's why the outlier totally dominates the computation. So therefore, in these new versions, we come up with some function like that. Even for large errors, the penalization is small. But for small ones, the penalization is there. So the contribution of the error of a large error, it sort of downplays by using this robustifying function. Nonlinear optimization problem that must be solved iteratively. Least square solution can be used for initialization. Scale of robust function should be chosen carefully. So there are problems. The scale of the robustifying function has to be chosen, things like that. And then it has to go through an iterative process because now the nonlinearity is there. These are the problems in using a robustifying function. But the effect of outliers is minimized, not totally gone. Not totally gone. So therefore, we have to robust fitting is okay, but sometimes still that is not sufficient. That's why we have to use RANSAC. RANSAC. Okay. RANSAC is a beautiful thing. It's called random sample consensus. Random sample consensus. RANSAC. So I will to explain you RANSAC. I will give you a brief, simple example of 1D case. Okay, but we are handling 2D. But this case we'll do a 1D one of the ransack. Give me a second. Okay, I want to draw something and show you. Assume the problem of okay, we want to estimate the height of a student by asking a question. All right, so now what I do is in this class, I ask one student, one student, I take this student. and ask him, what is your height? And he will say, I don't know, 43 centimeters. 143 centimeters. Then I ask, like, how many people like it? Vote. I ask people to vote. Let's say the class has 30 students. Out of them, only, okay, maybe I made a mistake. As in that due to some wrong reason, we picked a very small, short person. He said the height is 90 something. So we asked the 30 people in the class to vote, and only one person will agree. All others disagree. Is that a correct estimation of the height? That's not the correct estimation. Then what we say is, we ask another student, okay, different student, what is your height? And then she will say 143 or something. Then I ask people to vote. Who likes this? Let's say out of this 30, 24 people like it. So then I can take this number of 143 as the correct height. So we can see randomly sample a student, get his height, and get the consensus. Vote means a consensus, right? Vote here, vote means a consensus. So you can see randomly you sample, estimate what you have to estimate, get a vote, and see how many people like it. Now, after 25 people like it, after 24 people like it, we can get all the heights of 24 people and average it. Their heights, we can average it. That's how you get a estimate using random. So you can see outliers are directly gone because the outliers are the people who did not agree with this. I hope this example explains how random sample consensus works, but it is, uh, I took that only for the one-dimensional case, only estimating one number, the height. But in line fitting, if you want to estimate a line, you have two parameters. If you want to estimate a circle, you have three parameters, and so on. This is the kind of thing. Okay, any questions about this before I show the random sample consensus animation? This animation is very important. So any questions? Please do ask questions if you have. Please don't hesitate to ask questions. Okay. So I hope you're ready for the animation. This is an important animation. The little example that I took was estimating the height, that means one parameter. For a line, there are two parameters. Okay. Now let's do that exercise for this line fitting case. All right. Basic idea, let each point vote for all the models that are compatible with it. Hopefully the outliers will not vote consistently for any single model. The model that receives the most votes is the best fit to the image. This is an important mechanism that people understood. The animation is not working. Yeah, it's working now. So what we do is we randomly choose a small initial subset of points and randomly choose a small subset of points, fit a model to that subset. So like that in the previous case, we got the height of the person. So that is like fitting a model. Find all the inlier points that are close to the model and reject the rest as outliers. Find those who agree, the consensus. Do as many times and choose the model with the most inliers. This is the procedure. Okay, so now here's the animation. The least squares fit is horrible for something like that because of the outliers. So randomly you select a minimum subset of points. So here there you can see the minimal, so-called minimal subset is 1 and 2, 2 points. Why is the minimum subset a set of 2 points? Because to fit a line, you need 2 points. Then you fit a line, hypothesize a model, and then find who agrees. Actually, not many people agree, right? Only 1 or 2 people agree. Like these people will agree. These are the only people who will agree. This person will agree. All the others says the line that you're computing is too far away from us. Okay, here are the distances to these points. Perpendicular distance, they are very high, very high. So the line that we hypothesized with these two red points is not correct. So select the points that agree with the model. So the green ones are the ones that agree. We have some threshold for that. And then you estimate the line. That's horrible. Again, do the sampling. Again, assume that you made a mistake. Yeah. Then again, you sample. So here you can see again, it has made a mistake. And here, okay, finally we got two correct samples. And because of these correct samples, you have a nice consensus now. Lot of people agree. Lot of points agree. So you can see in this region, these points agree to the line confirmed by those two. Is that clear for you? Now that you have the consensus, from the consensus, you estimate the line using least squares, line fitting, or total least squares. I hope this idea is clear for you. Okay, you keep on doing that until you get the best one. So repeat n times. Okay, now let's look at the algorithm. Repeat n times. Draw S points uniformly at random. Fit the model to these S points. S points means here we have to select S equals 2, right? Because you need 2 points of the line. So this theory is not only for a line, but for other structures also, maybe fitting a circle and so on. So therefore, that's why they have put a symbol S, fit a model to these S points. Find inliers to the model among the remaining points, inliers, those that agree. So point whose distance or residual with respect to the model is less than some t. If there are d or more outliers, exit the model and refit using all inliers. So you can see it's a beautiful theory. So now choosing parameters is a thing. Initial number of points, typically the minimum number needed to fit a model. For a line, it's 2, for a circle, it's 3, and there are little bit of different structures where you need certain number of points, and we know those things. Distance threshold for T for inlier. So what do you call an inlier? So points that are within 3 threshold of the hypothesized line, right? Distance threshold. Need suitable assumptions. Example, given zero mean Gaussian noise with the standard deviation sigma and t equals to 1.96 sigma will give 95% probability of capturing all inliers. So you can see this threshold, whether we take them as consensus or reject them from the consensus, has to be carefully chosen. Consensus size D, how many points do you want to be in consensus? So this should map the so-called expected inlier ratio. We will discuss about that, and the number of samples. How many times do you do this sampling? Choose and so that the probability P, at least one random sample is free from outliers. P is 0.99. There's a question. I will answer that question after completing this slide. Okay. Now I want to find a relationship between the outlier ratio and the number of samplings that you had to. So assume that you believe that the uh, percentage of outlier, so percentage of erroneous samples is something like 40% or something, 0.4%. So based on that, we can say, before we start the experiment, how many times at most we will have to do the experiment if you want to get the parameters within um, some confidence interval. Okay. All right. That we will say. Okay, this is the formula, but I need to show how to derive that. So we are computing this by n. Outlier ratio. That is E. Then if in outlier ratio, for example, 40%, then inlier ratio. Sorry, inlier ratio 1 minus E, right? 1 minus E. That's the inlier ratio. Like 60%. Then if we want have to pick S points. S points. Example, S equals 2 for a line. Probability of all S points being inliers is equal to 1 minus E, that's the inlier ratio, to the power of S. Do you agree with that? Because first point has to be an inlier, second point has to be an inlier. So you have to multiply 1 minus is together. If you have to pick 4 points, first point has to be inlier, 1 minus C. Second point has to be inlier, 1 minus C. Third point has to be an inlier, 1 minus C. Fourth point has to be an inlier. Yeah, okay. Okay. Inliers. Okay. Probability of the sampling sample of S points being contaminated. That means having outliers. That is 1 minus this one, right? 1 minus 1 minus C to the power of S. Okay. That's okay. Would be right from here. Okay. Probability of of all n samplings being contaminated. So this is just for one sampling. If all n are contaminated, you are in deep trouble. 1 minus e to the power of s, and all n are corrupted. So this is probably to the power n. All n are corrupted. Okay, so this is very bad situation. All n are corrupted. So at least one sampling being free of contamination equal. So that is 1 minus this one, 1 minus this one. This one. Okay. So this is the probability that you want to achieve. So you can see this is the probability that you want to achieve. So if you want, if we want with probability P, at least one sample will be from outliers. So we have the equation now. This one must be equal to 1 minus P. So the probability when this bad thing, total bad thing can happen, 1 minus P. So therefore now we can compute N. N equals, we have to get the log, right? Log 1 minus P divided by log this. Just a parenthesis. Yeah, this is how you compute how many times that you have to sample to get at least with 1 minus P probability, at least with P probability that we get a correct, at least correct, one correct sampling. So if we set P equals 99%, 90.9% of the time, we will get at least one correct sample if we do n samplings. That's the idea of that. So here is a calculation of that formula. If we take the line detection case, line estimation case 2, and if your inlier ratio is, for example, 40%, we have to do 11 samplings to ensure 99% of the time being at least one uncontaminated sample being there. So you can use that formula to do this calculation. I will not do an example calculation. Uh, you can do an example calculation. It's very easy. Use that formula. Maybe I will do one. Otherwise, I'll do one example. All right. So the task is do an example. So let's consider P is equal to 0.99. S is equal to, and E is equal to outlier ratio 0.4. And we are considering this case, right? So let's apply the formula. N equals log 1 minus P, that means 1 minus 0.9 divided by log 1 minus 1 minus 1 minus E 0.4 to the power of 2. Oh, you did not properly write the formula. I'm glad that the whole thing point is this. So this is wrong. Okay. I'm sorry about that mistake. I hope everything's clear. I'm glad that we did start doing this example, otherwise I will not correct. So let's quickly do that. I'm sorry about the time waste. So 0.99. This is to, again, this n is not there. This log thing we got that. Is 0.4. This one is 0.6 to the power of 2, right? So what you get is n equals 0.01 log divided by log 1 minus 0.6 to the power of 2. You can do that calculation by the calculator. Battery is gone. Yeah, I hope this clear. So because 1 minus 0.6 squared. I hope this is correct. I don't want to make a mistake here. 10.3. That's what 11 means, right? So I hope it is correct. I hope you understood that. When S is equal to S. Let me correct that formula here. I know what's happening with this n. I cannot delete. It's correct. So what you can see in this case, when outlier ratio is large, the number of iterations that you do seriously enhances. That's the radius becomes large. That's the problem. So question, so when SIFT compares the pixel patterns and guesses the transformation, then go to ransack, is there a way to faster the process by the initial guess by cone or something? Otherwise, more data points and more compute leads to best accuracy, right? Yeah, that's a good question. I think the question is about when you have to use ransack to filter out the incorrect point matches or something, is there a way to better the point matches so that you can do it faster? Yes. So you can take other measures like likelihoods, probabilities, and so on of good point matches. If the inlier ratio is increased, then the number of iterations that you have to run seriously reduces. And one more question. And from this method, let's say that since we are using the brute force kind of method, is there a few guessed transformation matches, assume the different rotations um, that will go over base iteration? Yeah. I hope I understand the question. Okay, let me briefly explain how this has to be done if you want to do SIFT for point matches. Now, assume that you have in the first image and the second image um, these 4 points or something. These 4 points in the first image. In the second image, something like these 4 points. So we are given that the point matches are this matches with this matches with this matches with this matches with this. Okay. So what we want to do is to compute a transformation that changes this image and matches with this image like that. Warps that image and matches with the points. That's what we want to do. So this transformation called H, it needs 4-point matches. If the 4-point matches are there, computing H is a closed form solution. We know that. We know how to compute that. For a line, what is the thing for a line? For a line, we need 2 points. This is a matching case. This is a model computation. This is also model computation through matches. This is a model computation through points themselves. So that model computation needs 2 points. This needs 4 matches, not points. But when this is done and this is given, computing the line is straightforward. It's a closed form solution. This one is also more or less a closed form solution. So if you can do the sampling, computing the model is a closed form solution. So what we are saying is when you do the sampling, if matches are incorrect, how to remove that problem? When you take these 2 points for the line computation, if these are not correct, if there's an outlier somewhere here, how do you get rid of that problem? There is no way to handle that. There's no way to handle that analytically. Only way is to go through this robustifying algorithm called RANSAC. Okay, there is a slightly better one called MLESAC. I think it is, okay, I think maybe this is the answer to your question. MLESAC. That actually use the likelihood of matches to improve the matching. So these are very important questions. This is the MLESAC paper. It's, you can see Philip Toe's paper. It's a large number of citations. It talks about some likelihood based see the same thing that we are discussing, based RANSAC. So it talks about RANSAC and talks about the MLESAC. So maybe I should add that to the WhatsApp group or something. So if you know about MLESAC, the paper says I have read that paper, I think. There's no reason to use RANSAC. MLESAC is better. So I hope this question is answered. So it's simple and general applicable to many different problems, often works well in practice. Bad things, lots of parameters are trained, doesn't work well for low inline ratios, too many iterations, or can fail completely. Can always get a good initialization, can't always get a good initialization of the model based on the minimum number of samples. Yes. So RANSAC is done. Then we'll briefly look at half transforms. Before 5 minutes are left. Maybe not. I will talk about the half transforms later. Yes. So if you have any questions, we can discuss, or maybe I can show you the answers to some of the quiz questions. I'll show some answers. I'm very happy about that question though. Okay. What is the primary goal of edge detection in an image? So that was a question. So increase the image contrast? No. Identify sudden changes in image intensity? That's correct, right? Edge detection means you find the gradient, points that have high gradient. That means sudden changes in the image intensity. Remove noise from an image incorrect, reduce the image size incorrect, enhance colors incorrect. Okay, second question. Which of the following is not a common cause of edges in images? So what results in edges? We had this slide, right? Object boundaries, it results. Illumination changes, yes. Texture changes, yes. Compression artifacts, yes. Uniform background does not give any edges. So answer is E. In discrete images, partial derivatives can be approximated using, so how do you get the partial derivatives? Fourier transform, finite differences, color histograms, principal component analysis. Components analysis is wrong. Half transforms, actually finite differences. In a smoothing filter such as Gaussian, the sum of filter values should be, of course, 1. What is the reason for that? Otherwise, if you run the averaging filter, okay, consider this. If your filter values sum to 2, you run the filter on all full bright. That means all values are 255, 255, 250, and so on. And then you multiply them by 2, the average multiply by, you multiply with these numbers and sum. If that sum is 2, so finally you will get 255 times 2. That cannot be represented using the number representation mechanism you indate in this case, right? So because of this reason, the smoothing filters must sum to 1. in the derivative filter, the sum of the filter should be, in a derivative filter, now if you take the white wall, no edges. If you apply the derivative filter to the white wall, it must say no edges. That means the output should be 0. That means white wall means all the numbers in the kernel are multiplied by the same value. Let's say white wall 255 or a gray wall 100. So therefore you can see they must add to 0. Okay, the discussion. In Canny edge detector, non-maximal suppression is used to, non-maximal suppression used to thin the edges, right? Increase the gradient magnitude, link broken edges, reduce ridges to a single pixel value. That we are studying, right? Remove low frequency noise, normalize gradient, that's no sound correct. Okay, we did 1, 2, 3, 4, 5, 6 questions. Yeah, since the time is running out, I will not do more questions. But if you have any questions, you can, I will answer. Otherwise, we will stop for now. So you may log off. Thank you very much for joining on a long weekend. So I wish you a happy rest of the weekend. You may log off if you do not have any questions. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.